Torricelli's theorem. Here one container is filled with liquid. It's not completely filled. You still have to keep two things in mind. One is the top of the liquid surface and the other the height or the length of the container. 2 points have been considered over here. One is the free surface. One point we are going to consider at the free surface and the other is at the outlet. You see, at both the points, it is the access, clear access to the atmosphere. So, you could say both are subjected to the atmospheric pressure. Now, two terms will be written as same P1 and P2. In Bernoulli's theorem, you have three terms. First term, that is pressure, it's going to be common at both. Then half density V1 square, half density V2 square. At one very point, this is at rest. So, this term also gets vanished. Second term only is left over here. This height is that of this point, that is the height of liquid column, and this is the height of the orifice, or you might say the opening. You take the difference of the two, that is the height of concern for us. Now, if you consider this point as reference level, h, height of this free surface is going to be the height of concern, and that will get the relation for velocity of efflux, that is root 2 gh. By using Bernoulli's theorem at the 2 points, we have concluded this result. This is known as velocity of efflux. This is the velocity of the liquid coming out from the opening at the wall of the container, which is at a depth h below the free surface. This you have to keep in your mind, that the height that we are considering is not in fact the height of the hole from the bottom. This is rather depth of this hole from the free surface. So, you could say the velocity of efflux for a liquid coming out from orifice at a depth h is same as the velocity gained by the body in falling freely through the same height. In fact, this analogy, this similarity is given the term Torricelli's theorem. Once again, I'll repeat. The velocity of efflux for the liquid coming out of the orifice at a depth h is same as the velocity gained by a freely falling body in height h. This is called but Torricelli's theorem. Torricelli's theorem is very good in that case when the liquid or the container is at rest, and when it is in motion, then also it has a little modified application. You see, now by taking this orifice at different position, we could calculate the range that we are going to represent by letter x. This will find equal to h minus h. What is h? Again, I'll repeat. H is the depth of liquid opening or orifice from the free surface. This is, remember, not the height of the container. This is height of the liquid column, total height. You might say this is capital H. Here I have shown capital H. Now, depending on the situation of orifice, you could have different ranges. It's very fascinating that when the hole is quite in the middle, this range is going to be maximum. In that case, this will be equal to height itself. How? You just put this small h equal to h by 2. Again, in place of small h, h by 2, you'll get this h by 2, 2 times take a square root, you'll find finally h by 2, and 2h by 2 obviously stands for h only. So, maximum range that is possible from any container when the opening is quite in the middle, the range is going to be the maximum. One more very interesting aspect of this velocity of a flux is that when you choose the hole from depth small h from the free surface, or other time you take the hole at a height small h from the bottom, in both the cases the range is going to be same, but naturally it's not going to be greater than total height of the container. Remember, total height of container is h, then in that case the maximum range possible is going to be h only. And finally what remains is the time taken in emptying a container. I have drawn the figure you see here. This is the cross section of the container, capital E. And suppose you have chosen the opening at the bottom of the container and that has the cross section A. Then through this hole, the liquid will obviously leak through. We have a formula for time taken in completely emptying the cylinder that is given by this relation. It's not given on the text page, but this is the actual formula that's taken when the column reduces from H1 to H2. Suppose the initial height is h, this becomes root h. Initially the height was h, suppose, as it is shown over here, and you are interested in finally emptying the cylinder. Obviously the final level is going to be 0. Then what remains is this much only. Then in that case the formula in completely emptying the cylinder is going to be this one. This is what exactly I have written over here, A upon A0 root 2 H upon G. You could say this is the complete time that the cylinder will require in getting completely empty.